Yeah, screen is visible now, right?
Sure.
Screen is visible.
Yes, sir.
Okay. Let me check just a minute. Fine, so I have given two questions like this. One you have this tosyl, then you have here NH, here you have nitrogen double bond carbon, this side you have methyl group, and here you have CH2 whole 5 CH3. Fine, so here if we use this two equivalent of butyl lithium in presence of ether, okay, so that time what will happen? So initially this butyl lithium, so okay, so butyl minus will abstract a proton from here, okay, so you are getting here N minus nitrogen double bond carbon, this side you have CH3 CH2 whole 5 CH3. Now this negative charge is basically is in conjugation with this double bond. So what will happen? You can draw like this: tosyl nitrogen double bond nitrogen. Here you have carbon. Carbon is getting negative charge. Here you have CH3, CH2 whole 5 CH3. That is the thing. Now so this is your one equivalent of butyl lithium we have used steel. So you have another equivalent of butyl lithium. Now the question is, from which side this butyl minus will take up the proton, from this side or this side? So which side it will take? From which side it will abstract the proton, from this methyl or from this CH2? Okay, this negative charge you can show it like this lithium, okay, because lithium is positively charged, carbon automatically will get negative. Now the question is, the second equivalent of butyl minus, it will abstract the proton from where? This proton or this proton? hmm? Which reaction it is? Which reaction it is? Am I audible?
Voice is breaking through.
My voice is breaking. Okay, check. Okay, just a minute. Yeah, now it is fine now. Am I
Yes,
audible?
sir, fine, sir.
Fine, right? Okay, fine. So if you use another equivalent of butyl lithium, so that time the butyl lithium will abstract the proton from this side. Why? What is the reason? Still breaking?
No, sir.
Okay, so yeah, from which side it will abstract the proton? Butyl minus this side, left side or right hand side? Left hand side, right? Left hand side. Why? What is the reason? Because this butyl lithium, keep in mind, butyl lithium means what? This is your butyl lithium. 1, 2, 3, 4. 4 carbon atoms you have. So this is your butyl lithium. Okay, it's a bulky base. Okay, first of all, it's a bulky base. Okay, second thing, which reaction it is? Shapiro reaction or Bamford-Steven? Which reaction it is?
Shapiro reaction.
So Shapiro reaction, what will be the product? In Shapiro reaction, you will get the less substituted alkene. Okay,
Less substituted.
less substituted you will get. So that is why that will be your main product. So what will happen next? This CH2 minus, that will back its electron to here, this bond, this nitrogen bond will break. Okay, so nitrogen gas is releasing, and tosyl is a good leaving group, so it is also leaving from this compound. Okay, so what actually you are getting? Ultimately you are getting this CH2 double bond carbon, you have lithium, then you have here CH2 whole 5 CH3, and what is releasing from here? Nitrogen gas is releasing, as well as your tosyl is a very good leaving group, so tosyl minus is also releasing. Okay, so what you are getting from here? You are getting less substituted alkene. Okay, if you are doing Shapiro reaction, that time you will get less substituted alkene. If you are doing Bamford-Steven, that time you will get your more substituted alkene. Clear?
Yes, sir.
Done. So you have this. Initially you are giving this Ar, SO2, NH, NH2. So what will happen? What will be the product from here? What will be the product? Kaveri? Kaveri, what will be the product
Yes, sir.
here? You have seen the recording lecture. Yesterday's lecture you have seen.
Sir, yes, sir.
Hmm?
Yes, sir.
So what you will get from
Yes,
here?
sir. So
Hmm.
we will get that one
Hmm?
more substituted alkenes. Sir. It is a
No,
Bamford
first.
Steven stick.
No. Initially, suppose this reaction. Tell me about only this reaction. I am not asking about Shapiro and Bamford-Steven now. Suppose you have this ketone compound and you have this hydrogen derivative. So what will be the product? Not getting. Suppose you are using
Bond.
tosyl hydrogen. What you will get?
Water will remove.
Water you have to remove,
No,
no?
sir.
Or
Yes, sir.
you can do by mechanism also. NH2 will attack here, this bond will break, ultimately it is becoming OH and you are getting nitrogen NH here, and you can release water from there also. So basically you can do in one step that water will release, so remove oxygen from here and H2 from here. Okay, or you can write down another time like this: NH SO2 here. So what is releasing? This part, water is releasing. So when water is releasing, now attach this part with your nitrogen. That's it. So now attach it, double bond in. Then what you have? NH SO2 Ar. Okay. This is the thing. Now if you use two equivalent of butyl lithium, so what you will get? So initially one equivalent, you are using two equivalent, so one equivalent will abstract. First of all, what is the most acidic proton here? Which one is the most acidic proton? This NH proton. So butyl minus will take this proton, okay, and I am showing in one step. So that bond will cleave to here, and this bond is in conjugation, so that will also break. So ultimately what you are getting, so here we are getting what? Nitrogen, double bond, nitrogen, and here you have SO2 Ar. And see, butyl minus is taking the proton from here. Ultimately the electrons are coming to this carbon atom, so that means here you will get one negative charge, okay, negative charge you are getting, and lithium plus is the cation part, so lithium plus will present here like this, okay. So this is your one equivalent of butyl minus is abstracting this proton. Now the second butyl lithium, you have another equivalent of butyl lithium, so that will abstract the proton from which position? That is the question. This proton or this proton? Which proton it will abstract? Which proton it will abstract?
Half on, sir.
Why?
Uh, it is a bulky base, sir. So
Okay, that is one of the reason. Yeah, bulky base, that is one of the reason. Yeah. So for butyl minus, it is easy to abstract this proton. Yeah, that is one of the reason. Another is, if you abstract the proton from here, I already mentioned in carbocation also that this is your bridging position, right? So this position is your bridging position. So you cannot form any carbocation, okay, or double bond in this bridging position, because this is not following your Braid's rule, okay. Braid's rule is violating here, so you cannot form any carbocation or double bond in this bridging position. Clear? That's why if you abstract this proton, na, if you abstract this proton, so that means carbocation, carbon, you are getting carbon ion. So carbocation or carbon ion or double bond is not possible in this bridging position, okay. This is violating your Braid's rule. So that's why this proton is abstracted by your butyl minus, and once this proton is abstracted, what you are getting? See, this bond comes to here, nitrogen is releasing from here, and this is your SO2 Ar, which is a very good leaving group, tosyl group, so that is leaving from here. So what we are getting basically, so you can form a double bond here, okay, and this side you will have lithium. Clear?
Sir, what is the stereochemistry of lithium, sir?
If you have double bond, that means this is planar, so here no need to show above the plane or below the plane, okay. If you have double bond, so that means the angle is 120 degree, it's a trigonal planar shape, this bond and this bond, these are in the same plane, okay. Double
Okay.
bond means what? Double bonds means sp2 hybridized, so this is a planar system, okay. If you have triple
Okay.
bond also, this is a linear system, okay. So stereochemistry only you need to check when you have only single bond on those things. Double bond, that means this lithium and this bond, they are in plane, okay. Fine. Now last is your CH3Br. CH3Br, so lithium is positively charged and this carbon center is negatively charged, right? So what will happen? This negative charge will attack on the carbon center, bromine will leave from here. So that will be your final product. This is a SN2 reaction. Okay, this last reaction is basically your SN2 reaction. Okay, this is a SN2 reaction. So if you have carbon lithium bond, you can think lithium is a metal, so it will be positively charged, and this carbon center will be negatively charged. That will attack from the backside of the carbon, and yeah, so basically it will act as a nucleophile. Okay, it will act as a nucleophile. Clear? Okay, just a minute. Yeah, clear? This one clear? Any doubt?
Yes, sir.
Clear, all of you clear, right? See, this Bamford-Stevens reaction and Shapiro reaction is important. Okay, they ask so many times as an intermediate question. They will ask this. Okay, so keep in mind those things. Okay, now next we have uh, Eisen-Moser fragmentation. Eisen-Moser fragmentation. Okay, fine. So you have this. Here I am using this reagent H2O2 in presence of NaOH. Tell me what will be the product?
Epoxidation.
Hmm? Epoxidation, right?
Epoxidation.
So this is your alpha beta unsaturated carbonyl compound. Okay, first of all, see what is this. This is your alpha beta unsaturated carbonyl compound. So that means this double bond is becoming what, electrophilic in nature, and in this H2O2 NaOH, what is the generating nucleophile you will have? You will have this nucleophile OH minus. Mechanism we have done when we have discussed H2O2 NaOH. Okay, so I am not showing the mechanism. It will do epoxidation of this double bond. Okay, so if you have alpha beta unsaturated compound, that time we will use this reagent. If you have only electron rich double bond, that time you can use your MCPBA and the other peroxide reagent. Okay, so epoxidation will take place. That will be your product. Next, what they are giving? Next, they have using this reagent tosyl hydrazine. So what will happen in presence of tosyl hydrazine? What will happen?
Water.
Water will release, right? So release water, then check what you are getting. Release water and write down the product. So oxygen from here, H2 from here. No need to change anything. So double bond N, then you have NH tosyl. That one you are getting. This product all of you are getting.
Yes,
Yes,
sir.
sir.
Okay. Now suppose you have this potassium tertiary butoxide, which is a base. Okay, potassium tertiary butoxide. So what will happen now?
Abshakta proton.
Proton. Which proton?
NH proton.
NH.
NH proton, right? So this tertiary butoxide is abstracting the proton, so initially you will get here negative charge. Now see, I am showing in one step only, or okay, I am showing in, you can show in different step or one step also. Okay, so if it abstracts the proton, what you will get? You will get here negative charge, right? Now see, this negative charge is in conjugation with this double bond, right? So show the conjugation. Negative charge is coming to here, this double bond breaks to here, and three membered ring is a strained ring, so this epoxide ring will open. Clear how it is in conjugation? So this negative nitrogen is giving its electron pair to this bond. When it is giving to this bond, automatically this bond will break. Okay, and this three membered epoxide ring will also break. Okay, so what we are getting? So I am getting a double bond here. Okay, then what I have? Nitrogen, double bond, nitrogen. Here you have tosyl. Okay, and here you are getting what? O minus, right? Right or not?
Yes, sir. Right.
Clear. Now what can happen? So up to this, whatever we have done, this is not your SN-Moser fragmentation. Okay. Now the next step is your SN-Moser fragmentation. Up to that, what we have done? This is your epoxidation reaction. Okay, that already we have done earlier, epoxidation reaction. And second thing is what? Second thing is your hydrogen formation. So that is also we have done. So if you would react with your potassium tertiary butoxide, so that means it is your, suppose what, Bamford-Stevens reactions, one equivalent you are using. Okay, but when you have this kind of system, so what will happen? See, this O minus will back its electrons to here. Okay, this sigma bond will back to here. Okay, this sigma bond will break. Okay, ultimately nitrogen is releasing from here, and this tosyl group is also releasing. Okay, if you are not able to understand, so that time you can draw in chair form also, like this. So here you have O minus in this axial position. Now suppose here you have double bond. Okay, and what I have here, you have nitrogen, double bond nitrogen, then you have tosyl. So what is happening? See, so basically this is the double bond you have, sorry, this is the single bond you have. So O negative is back its electron density to here, this double bond shifts to here. Okay, nitrogen is also leaving from here, and tosyl group is also leaving from here. Okay, clear? You can ask me, sir, why
Yes, sir.
this sigma bond is breaking? So this is your sigma bond, so that means the anti-bonding orbital is present here. So for this O minus, it is very easy to donate the electrons in this sigma star orbital. When it is donating the electrons in the sigma star orbital, this sigma bond will break. Okay, this sigma star orbital is present here. Okay, so O minus can easily transfers the electrons in this vacant sigma star orbital, and when it donates, this sigma bond will break, and you are getting what? You are getting this kind of product. See what you are getting. So how to draw this thing? Just a minute. So this downside I am drawing first. So you have this, right? Here you are getting double bond O, double bond O. Up to this is fine. Now you have CH2, then you have carbon triple bond. Okay, so let me draw it. So suppose you have here CH2, then you have what? Carbon triple bond carbon. Okay, and then again you will have one CH2 here. Okay, that is difficult to draw here. Okay, I am showing here. So again you will have one CH2 here. Okay, and like that. Check one time, check from here. So suppose I am starting from here. So 1 2 3 4 5 6 7 8 9 10. Start from here. 1 2 3 4. Triple bond is between your 5 and 6, so I am getting 5 6 7 8 9 10. Yeah, correct. Okay, so triple bond is forming here. Okay, and suppose here I am giving this reagent now, hydrogen, and what, hydrogen, palladium, calcium carbonate in presence of quinoline. What will happen? What will happen? Which reagent? It is hydrogen, palladium, calcium carbonate, quinoline.
Lindlar's catalyst.
Lindlar's catalyst. So in presence of Lindlar's catalyst, what will happen? From triple
Triple
bond,
bond will reduce.
triple bond, what you will get?
Double
From
bond.
double bond is fine. Triple bond, you are getting double bond definitely, because you are adding hydrogen, so that means you will get double bond. But what will be the thing, cis or trans? If I use Lindlar's catalyst on alkyne compounds, what will be the thing? Cis alkene or trans alkene?
Cis alkene.
Cis alkene. So you will get this. Okay, these hydrogens, they are adding in the cis position. Okay, so cis alkene you will get, cis alkene. And how to get trans alkene from triple bond, from alkyne? How to get trans alkene? What is the reagent for trans alkene?
Birch reduction.
Barch reduction, sodium liquid ammonia. And apart from Lindlar's catalyst, what we can use to get cis alkene? Suppose you have carbon, triple bond,
Dival.
carbon. Hmm?
Dival.
Dival H, correct. So one thing is your Lindlar catalyst, you will get cis alkene. If you use your dival H, that time also you will get your cis alkene. If you use sodium liquid ammonia Barch reduction, that time you will get your trans alkene. Okay, so this you have to practice. Clear? Kaveri, Rakesh, clear?
Yes, sir.
Practice the reagent
Yes, sir.
chemistry. Okay, practice the reagent chemistry, otherwise you will forget. So many reagents are there. Okay, after finishing this thing we will practice questions. That time you can see how much practice it needed. Okay, otherwise you cannot remember a single reagent. After 5 days you will forget. Okay, so next is your NAF reaction. Okay, so what is happening by this NAF reaction? So if you have nitro compounds, okay, nitro compounds, so these nitro compounds will directly convert into your carbonyl compounds. Okay, nitro compounds will convert directly into carbonyl compounds. Okay, now suppose you have this nitro. Okay, Nitro. So if I use this reagent, what is your NAF reaction actually? What are the reagents we are using? So titanium chloride in presence of heat, you can use that. Most cases we are using titanium chloride in heating. Okay, sometimes you can use H2SO4. Okay, heating, but this H2SO4 heating actually most of the cases they will use this titanium. Or sometimes they can give you like this also, NaOH, sodium ethoxide, okay, in presence of sodium iodate, NaIO4, sodium ethoxide in presence of sodium iodate, okay. Or you can use NaOH, sodium ethoxide, okay, and second reagent will be what? O3 PbH3, ozonolysis. So no need to worry. Okay, most of the cases they are using this titanium chloride heating. Okay, they are not using this reagent that much, because students will become confused, so they give you straightforward this titanium chloride heating, because this is a not that much common reaction, NAF reaction, so they gives you the hint, they give you the hint. Okay, titanium they will use, and if you have titanium, so directly you will get your secondary ketone compound. Okay, if you are using this reagent from nitro compounds, you will get carbonyl compounds directly. Clear? This is the only thing. Fine. Okay, next we have Corey-Winter reaction.
Previous one mechanism also.
Mechanism. Okay, mechanism I will show. Actually there is no proper mechanism still yet they have discovered. Okay, so they give one mechanism from one research paper, but yeah, I will show you. Okay, let me search here. But this mechanism I really don't prefer, because so many controversy are there. You can see here this mechanism also. Okay, okay, so this mechanism you can follow. But it will be actually little bit difficult, that's what I am avoiding this mechanism, because mechanism part you will get only one thing here, you will get only your this is the research paper you can follow.
So,
Okay, but this mechanism will be little
so,
bit difficult, that's why I am avoiding. Otherwise, and there is no like there is no probability of getting another product or something like that, you will directly get your ketone compound, but for interview purpose you can definitely follow this mechanism, because interview sometimes they can ask what is the mechanism. Okay, and this is the paper you can follow, this 2017 Roman A value in. Okay, this paper you will have, I think chem science they have got in this. Okay,
so,
this is your Prince reaction, those are not we are discussing. Fine. Okay, so next we have Corey-Winter reaction. So in Corey-Winter reactions we have 1 2 diols 1 2 diols in presence of PPH3. Okay, in presence of PPH3, so you have 1 2 diol. 1 2 diol means vicinal diol, basically gem diol and vicinal diol, and you will get alkene compounds from here. So if you have this kind of thing, suppose you have this, here you have OH and here you have OH, this is actually known as your vicinal diol. What is vicinal diol? So if two carbon have, like two adjacent carbon have OH, that time it is your vicinal diol. And suppose the two alcohol groups you are getting from only one carbon atom, that time it will become your gem diol. Okay, so that is the basic difference between your gem diol. Gem diol means both the OH groups are attaching with a single carbon atom, and vicinal diol means the OH groups are attaching with different carbon atoms, with the adjacent carbon atoms. Okay, so if you use this kind of 1,2 diols, which is actually basically your vicinal diol, okay, so in presence of PPH3, what you will get? You will get alkene compounds. Now suppose I am using here this reagent, okay, carbon double bond sulfur, here you have OET, and here also you have OET. So what will happen? Oxygen has lone pair, right? Oxygen has lone pair. So what will happen? Oxygen will attack on this carbon, okay, this bond will break, okay, again this will come back, ultimately this OET group will release from here. So what I am getting are, okay, then you have oxygen here, then here you are getting carbon, what, double bond sulfur, one OET left, and here you have OH. So here also you have lone pair. Now what will happen? Next step, tell me. Next step.
OIT
In the
Hmm?
OIT
again the
will
lone pair
remove.
attack the carbonyl carbon and it will.
So again the same thing. This bond will break. Again it will come back. Oh, it is a good living group. It will leave from the system. So what I am getting? I am protecting actually. Okay, this is actually a protection reaction. Huh? You are protecting the diol. Okay, so you are getting this. Now you have PET3, right, or PPH3. You can use any phosphor, triethyl phosphine or triphenyl phosphine, anything you can use. Okay, so suppose you have this. Now tell me what will happen. What will happen now? What will happen now? So keep in mind this. I told you already that if you have this phosphorus oxygen bond or silicon oxygen bond, these are very strong bond, right? Here also sulfur is also your what, group member of your oxygen, right? So that means sulfur is also electronegative. So this phosphorus will attack on the sulfur atom, don't attack on the carbon atom. Many students actually did this, they attack on the carbon atom, then they are not able to get what they will do next. Okay, because if you attack on carbon atom, then it is finished, you cannot move now. Okay, so what you have to do, it will attack on the sulfur atom. Okay, similar thing, phosphorus oxygen bond is strong, similarly your phosphorus sulfur bond will be strong, not that much strong, but yeah, comparatively strong to your phosphorus carbon bond. Okay, and sulfur has vacant d orbital, so it will occupy these electrons, and once it attack on the sulfur atom, this bond will break. Okay, this bond will break. So here you have oxygen, oxygen, carbon. Okay, okay, this is carbon, huh? It looks like E, but this is your carbon atom. So here you have sulfur, and here you have PET3. So phosphorus is donating electrons, it will be positively charged, and carbon is getting electrons, so it will be which charge? Negative charge. Next will be what? Next step, can you tell me what will be the next step? Next step, so this bond will break now. If this bond breaks like this, so that means the electrons are going to your sulfur atom, right? So what you are getting? Sulfur minus and what? PET3 plus. So what I can write down? phosphorus, double bond sulfur, Et3. Check you are getting similar kind of thing what you are getting for Wittig reaction also. In Wittig reactions only you are getting oxygen here instead of sulfur. That is the only change, right? Right. And carbon will get which charge? Carbon, huh? Carbon will get which charge?
Neutral.
Neutral, right? So positive charge, so that means carbon is forming here. Okay, carbon formation is happening here. Okay, carbon is forming here. That is the thing. And once your comes this radical chemistry, now you can guess what will happen. So see, this carbon oxygen bond, if I break, if one oxygen moves to your oxygen center and one oxygen comes to your carbon center, and here also one oxygen moves to your oxygen center, one oxygen comes to your this carbon center. So what actually you are getting? Check what you are getting. If I write down like this, so you are getting like this: O dot, O
Or
dot,
double bond or
huh? What is the
double bond or
so that is what is the product?
alkene compound.
Hmm. This thing you are getting, right?
Yes, sir.
So now attach these odd electrons. What you are getting? CO2, and this is what? This is your alkene. Okay, CO2 plus alkene you will get. Okay, write down in like this: CO2 plus what you are getting? CO2 plus alkene compound you are getting. Clear?
Yes, sir.
Clear, sir.
Any doubt? Any doubt?
No, sir. Clear, sir.
No, right, fine. Okay, do this question. Suppose you have this is the compound you have. Try to solve it, huh? All of you try to solve it. Write down the product. Same thing you have to do again, but do it. You guys try to do it. Then tell me what you are getting as your product. Do it, then tell me what you are getting. So after the first step, what you will get after the first step? What will happen? So OH has a lone pair, right? OH has a lone
Yes,
pair.
sir.
What will happen? OH will attack on the carbonyl carbon. This bond will break. Okay, if you have carbon double bond sulfur, so this is similar to your carbon oxygen double bond. Okay, carbonyl bond. So it will again back and chlorine will leave from here. Then in the next step, what will happen? This OH has also lone pair, so that will also attack on the carbon center. Again, that thing will happen and chlorine will leave from here. So ultimately, what you are getting? Ultimately, oxygen, oxygen. Here you have carbon and double bond sulfur. Okay, that is the thing, right? This thing you are getting or not?
Yes, sir. Getting.
Getting, right. Next will be what? In presence of PET3, PET3 or PPH3, same thing. Okay, triphenyl phosphine or triethyl phosphine, same thing. So it will attack on the sulfur atom. This bond will break. Once this bond breaks, what I am getting? So sulfur is here. Here you have PET3. So phosphorus is donating electrons, it will be positively charged. This carbon is getting electrons, it will be negatively charged. Okay, so what I have here, OCH3. Okay, here you have OBN and this side you have CH3. So after that, what will happen? This bond will break, and once this bond breaks, what you are getting? You are getting what? Carbene compound. You are getting carbene compound here. Okay, then this bond will break like this. So ultimately you will get what? Alkene compound. Okay, ultimately you will get alkene compound. Attach the substituent here, whatever the substituent you have, attach them, and that is your product. Same mechanism, nothing I am changing, just do step by step, you will get your product. Okay, anything I am changing here in the mechanism? See, with the previous mechanism, anything I am changing here?
No, sir.
No. Clear? Kaveri, clear?
Yes, sir.
Clear, right? Tell me any doubt in this mechanism or in question, any doubt you have from this Corey-Winter reaction. Corey-Winter reaction is also important. Okay, all the reactions are important. We cannot say this is important, this is not. Important reactions we are doing only. Clear? After getting this carbene compound, you have to release CO2 from here. Okay, you have to make it release this CO2 gas, and if you release the CO2 gas, automatically one alkene compound will form from here. Okay, done. Okay, try to do this one. Phenyl, then suppose you have here also phenyl. Do this one. So first of all, keep in mind in this Corey-Winter reaction, whatever you are getting one two diols, this diol should be present in the same side. Okay, not on the opposite side. Then only you can do your Corey-Winter reaction. Okay, both the OH groups should be present on the same side. Here also, if you see, both the OH are present in below the plane. Then only they are doing reaction. But here, if you see, one OH is present above the plane and one OH is present below the plane. Right? So what you have to do? First of all, you have to rotate the bond. This is your carbon-carbon single bond, so you can rotate via this bond. And if you are rotating this bond, that time only the OH will come in front or this OH will go in below. Right? So that thing you have to make it sure that your both the OH should be present on the same side. Otherwise, there will be no fate of your Corey-Winter reaction. Okay, it cannot proceed. So if you rotate via this bond, suppose I am rotating only this front carbon, so what will happen? So suppose OH is going to, okay, I am drawing here. So okay, if I draw it in your Sahor's projection, how it will look like this? Suppose you are watching the molecule from this side. Okay, you are watching the molecule from this side. So here you have phenyl, this phenyl. So this is the skeleton. You have phenyl, this phenyl. Now see, OH is above the plane, so that means what? OH will be in right hand side or left hand side?
Right hand side.
Right hand side.
Right and six.
Hydrogen will be left hand side, and in the this carbon, hydrogen will be in the right hand side, OH will be in the left hand side. Now rotate in such a way that OH should come in like sine position. Okay, that you have to rotate like this. Okay, so suppose I am rotating by 60 degree for this OH, and this OH I am rotating by 120 degree. So that time what you will get? This OH is coming to here, this OH is also coming to here. When I am rotating like this, so that means pH is going to here, hydrogen is coming to here. So I can show like this. And if you rotate like this in clockwise direction, that time nothing is changing. Hydrogen will be in the right hand side, phenyl will be in the left hand side. Right? Clear?
So,
Yes,
So
sir.
now you do the reaction. So after this rotation you are able to do the reaction. Okay, not before that. So now do it. So OH will attack here, chlorine will leave from here. This OH will attack here, chlorine will leave from here. So what I am getting? So here I have oxygen, here also I have oxygen. Here what I have? Carbon, double bond, sulfur. Now see, phenyl is present in left hand side, so I am showing directly that phenyl as you are below the plane. Okay, and here also phenyl will be below the plane. I am not showing hydrogen. Hydrogen will automatically above the plane. Okay, clear? After this step, they have given this reagent. So see, they will give like different structure like things. So no need to fear anything. Okay, they have given this instead of this triphenyl phosphine, they have used like this. So this is also your phosphorus compound. So phosphorus has lone pair, so phosphorus will attack here, same mechanism, this bond will break, ultimately you will get carbene, and what you will get thing like this. Both pH are in the below the plane, so pH will be cis to each other, hydrogen are cis to each other, so you are getting this compound. Clear? Any doubt? You can write down the
yes, sir.
reagent here only. Okay, you can write down the reagent here because this is a previous year question. This is the full question. So this is your Corey-Winter reaction. You will get your alkene product from here, from the diol compound. Is it clear? Any doubt? Rakesh,
Yes, sir.
clear, sir? Clear? Sampradip, clear?
Yes, sir, please.
Clear, right? Okay, so we are done almost. We have two more name reaction. Okay, then we are done with this. So next we have Peterson olefination. Okay, this is very famous reaction, Peterson olefination. Okay, this reaction is also known as your Szila-Wittig reaction. Szila-Wittig reaction. So Peterson olefination, or you can call it Szila-Wittig reaction. So here we have actually two types of reaction. One is your base catalyzed and another one will be your acid catalyzed. Okay. So first of all, write down that if you do acid catalyzed, okay, acid catalyzed, you will get anti-product. Okay, anti-product. If you do base catalyzed, that time you will get syn product. How to remember? See, A is here, A is also here. So acid will be always anti, base will be ulta. Okay, base will be opposite. Okay, just remember for acid catalyzed, automatically you can remember for the base catalyzed. Okay, no need to remember everything. Fine. How to remember? A. Okay, A of your acid and A of your anti, both are matching. Clear? So first of all, give heading that
Yes, sir.
base catalyzed. Okay, base catalyzed we will do first. So here also the stereochemistry you have to do. So first of all, write down the compound C3H7. Here also you have C3H7. Okay, and here you have SiMe3. Okay, and here you have above the plane you have OH. Okay, and if below the plane, if nothing is given, so that means below the plane you have hydrogen. Here also below the plane you have hydrogen. Okay, now what we are doing, first of all, you have to make sure that this SiMe3 and this OH, they should be in the same plane. Okay, same side. This SiMe3 and OH, they should be in the same side. So again you can take help from your what, Fisher projection. Okay, sorry, Sahor's projection. So you can write down here C3H7. Okay, this is the main skeleton you have, C3H7. You are observing this molecule from this side. Okay, you are observing this molecule from this side. So here you have C3H7 above the plane, means that will go in the right hand side SiMe3, and left side you will have hydrogen, and here right hand side you will have OH, left side you have hydrogen. Okay, now rotate in such a way that SiMe3 and OH should be in the same side. Okay, rotate it. Suppose I am rotating it by 60 degree and rotate OH by 120 degree. Check what you are getting. SiMe3 I am rotating by 60 degree in the anti-clockwise direction. So what I will get? This thing you are getting, all of you are getting this thing. Check. Clear? This thing you are getting, all of you? Hmm?
SI M3 and OH group both are in above the plane.
Yeah, above the plane, na?
Yes, sir. Why will you rotate the molecule?
Above the plane, yeah, but this stereochemistry you have to bring in same side, na? You can do like this, but that will, what I can say, you can do from here also, but ultimately like it will like what, if you do like this na in the same side, that time it will become for easy for you to understand. Otherwise I can do from here also, but you will not understand properly. Okay, that's why I am showing it. Otherwise I can give the base
Sir,
from here and then I can do, but you will not understand properly. That's why I am rotating this. Okay, otherwise no need
the
to do.
second carbon, how do we rotate that? If we rotate 120-degree, then the C3H7 will be that
I am
left
doing
hand
it
side.
wrong. I am doing it wrong, right? Sorry. Yeah, I am doing it wrong. Thank you. If I rotate 180 degree, 120 degrees, so C3H7 will come here, hydrogen will come here. Yeah. Hydrogen is here, C3H7 is there. Yeah. Thank you. Okay. Now suppose you are giving here potassium hydride. So what will happen? If I use potassium hydride here, what will happen? Potassium hydride is what? Base, right?
Yes, sir.
So it will abstract the proton,
Yes,
abstract the,
sir.
yeah, do it. So H minus, potassium plus, H minus is abstracting the proton from OH, and what? You are getting here O minus. That's it, right? Now tell me what is the possibility, what you can do from here, from the here. Anything possibility is there?
Silicon oxygen bond.
Correct. Silicon oxygen bond is the strong bond. So if you have phosphorus oxygen or silicon oxygen, take a chance. Okay, O minus will donate the electrons in the vacant d orbitals of your silicon. Silicon has vacant d orbitals. Okay, no need to think anything. So silicon actually hold much more electrons than what you are expecting. Okay, so C3H7, and here you have oxygen. It's better to write down in this side. Okay, because show the bond properly. Ma3, yeah, hydrogen is this side, and here you have C3H7. So O minus is donating the electrons on the silicon center, so ultimately silicon is becoming now negatively charged. And once this silicon oxygen bond is forming, once this like you yesterday, once the phosphorus oxygen bond is forming, there also you are getting, this is your actually derivation of your Utic reaction. See, Sila Utic reaction, instead of phosphorus you are using silicon, that is only. That's why Peterson olefination is also known as your Sila Utic reaction. Utic reactions mean you are doing with phosphorus, but in Peterson we are doing with silicon. That is the only change we are doing. But see, here also you are getting a four-membered transition state. So once your silicon oxygen bond is forming, this carbon silicon bond will break, and this carbon oxygen bond will also break. So what we will get, see what we are getting. So hydrogen, here you have C3H7. Okay, double bond. Now see, here left side you have hydrogen in the front carbon, back carbon left side what you have, C3H7. So write down C3H7. Right side you have C3H7, in the back carbon you have right side hydrogen. So write down what you are getting. This is your cis or trans alkene, right? Trans alkene you are getting. Okay, so if you do base catalyzed, you have to remember this syn. Okay, syn means what? Syn means this oxygen and silicon you have to make in the same side. Okay, this oxygen and silicon you have to bring in the same side. Fine, clear?
The byproduct.
Byproduct is this Me3Si double bond O, write down. This is the byproduct.
Charge of silicon. Silicon charge.
Silicon charge will be neutralized, na? This bond is breaking to here, right? This bond is breaking to here.
Yes.
Okay. Clear, done.
Answer.
Understood? Any doubt in this mechanism?
Yes, sir.
Silicon charge will be neutralized, huh? This bond is breaking, so carbon is getting negative charge, silicon is getting positive charge. Already it has negative charge, so negative and positive is becoming neutralized. Clear?
Okay, sir.
Okay, so now next you have acid catalyzed. Acid catalyzed. Okay, so acid catalyzed, what I mentioned, anti, right? Acid means what? Acid means anti, that you have to remember. So I am giving the same kind of same molecule I am giving here. The condition will be different only. So suppose you have C3H7, here also you have C3H7, okay, here you have OH, and here you have SiMe3. Okay, now see what is the reagent I am using here. So H plus, that means acid condition, BF3 ether. Okay, so this BF3 ether is basically your Lewis acid. Okay, they are acting as a Lewis acid. Okay, so now tell me what will happen. So first of all, you can draw this molecule in like your previously what we have done. So C3H7, first of all draw the skeleton. C3H7, above the plane you have SiMe3, so that means right hand side you will have SiMe3, left hand side you will have proton. Here above the plane OH, so right hand side you will have OH, left side you will have hydrogen. Now what? Acid means anti, so you have to make here SiMe3 and OH anti to each other. Okay, do it. So nothing to worry, you just rotate 60 degree this SiMe3 and here also 60 degree to this OH. Okay, do it, you will get anti. So I am doing this SiMe3. Okay, I am doing here what? Anti-clockwise, right? So hydrogen will be in the left hand side, C3H7 will be in the right hand side. Okay, and if I rotate here, OH will come to here, hydrogen will go to the left hand side, C3H7 will be in the right hand side. That thing you are getting or not? Clear?
Oh,
So acid means anti, you have to make it anti. Okay,
Yes.
now what is the reagent we are giving here? H plus in presence of BF3, right? So if I give here H plus, what will happen? What will happen?
water release.
What?
Water release.
Water release. So OH will abstract the proton. OH will abstract the proton. So here you have SiMe3. Okay, this side I have what? OH2 plus. Okay, here you have C3H7. hydrogen. Here also I have hydrogen and C3H7. Okay, now basically water will release from here. Okay, and if you are using acid, so that means always keep in mind you have some amount of water present in that. Okay, because acid, concentrated acid, we are not using. Okay, we are making it dilute. Okay, 100% concentrated acid no one is using in lab also. Okay, you will use 98% or 99% like that only. So you will have some amount of water. So water will attack on the vacant d orbital of silicon. This bond will break, water will release from here. Okay, now see what will be the product. So here I think hydrogen, both the hydrogen are in the same side. So hydrogen, hydrogen, this side you have what? C3H7, this side also you have what? C3H7. So this is what? This is your cis-alkene. Okay, you are ending with cis-alkene. Clear? Clear? So basically
Yes.
you just remember this, that in acid catalyzed you will get anti-elimination. Okay, anti-elimination, and in base catalyzed you will get your scene elimination. Okay, okay, just a minute, I'm coming back, just a minute. हेलो, हाँ क्लास ले रहा हूँ, क्लास ले रहा हूँ। नहीं, क्यों? क्यों? अच्छा, हाँ ठीक है, ठीक है, आता हूँ, मतलब 5:30 बजे ख़त्म हो जाएगा मेरा, उसके बाद मैं निकलता हूँ। किसे? मुझे क्या खुशी में मिलता है? हेलो, मुझे क्या खुशी में, अगर आता तो मैं मिलता, लेकिन शायद, हाँ, हम्म, 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 हाँ, हाँ, हम्म, हम्म, हाँ, हाँ, हम्म, हम्म, ठीक है, ठीक है। हम्म, ठीक है, उसको पता नहीं था बैंगलोर का सिचुएशन, अभी पता चलना शायद। अभी क्या करोगे, फोर्सफुली तो तुम ला नहीं सकते हो ना, उसका आने का मन है तो आएगा। हाँ, उस पर छोड़ो ना थोड़ा, अगर उसको आने का, अगर उसको बुरा लगे तो कल तक तो आएगा ना, कल भी तो टाइम है। हम्म, अच्छा, ठीक है, देखो फिर आ भी सकता है। ठीक है, मैं आता हूँ, रुको थोड़ा, हाँ। अच्छा ठीक है, मैं आता हूँ। आता हूँ, हो गया है। ठीक है, आता हूँ, रुको थोड़ा, हाँ, 15-20 मिनट। फ्रेश हो जाओ, मैं आता हूँ, हाँ। ठीक है, खाना खाने जाओ फिर, खाओ कुछ। अरे नहीं रे, अभी किधर हो तुम? तो ठीक है, तुम थोड़ा बैठो, मैं आता हूँ। हम्म। ठीक है, রাখছি, हाँ। हम्म। Yeah. Am I audible?
Yes, sir.
Audible,
Sir,
right?
are you listening?
Yeah. Okay. So just remember this. In Peterson olefinogen, if you have acid condition, acid catalyzed, so it will be anti-elimination. If you have base catalyzed, that time you have to do syn eliminations. Okay, that's it. Okay, and this is the last one we have. Okay, this is the last one, last reaction. Okay, if I found some important name reactions later, so I will add here, because for in YouTube basically what I did, I have made different playlist. Okay, so there I will add. Okay, so no need to worry, it will not mix up with other classes. In playlist you will get in a proper sequence, you will get all the things. So next is your Julia olefinogen. Okay, Julia olefinogens. So write down one line that E alkene are formed E alkene are formed from sulfones and aldehyde. Okay, so E alkenes are formed, basically E alkenes are forming here. Okay, from what? From sulfones and aldehyde. Okay, so let's see the mechanism. We will directly go to the mechanism part. So suppose you have a sulfone, means this kind of thing, sulfur double bond O. Okay, double bond O. Here you have a aryl group. Okay, and here you have two proton. Next what you have? You have butyl lithium. So butyl lithium means what? Lithium plus, and here you have butyl minus. So what will happen? Butyl minus will abstract the proton. Okay, because this is your acidic proton. You can see here, after abstracting proton, the negative charge is in conjugation with the sulfur double bond O, right? So that is actually your acidic proton. So you are getting this negative charge. So this is your sulfone derivative. Now next is coming your aldehyde. So suppose you have some aldehyde. So what will happen? This negative charge will act as a nucleophile, and it will react on the carbonyl carbon. Okay, when it attacks, so what I will get, I can write down like this. So suppose this is your carbon, you are getting O minus here, hydrogen R, and this whole group SO2AR, this whole group is here, SO2AR. Okay, next step, suppose I am giving acetic anhydride. What is the structure of acetic anhydride?
CH3, C double bond O.
Then
CH3, C double bond O.
oxygen is there, na? It's anhydride
Then
only.
connected.
So O minus will attack on this carbonyl carbon, this bond will break, it will come back. Ultimately this OAC group is releasing from here. It's a good leaving group because O minus is in conjugation, it's a stable product. Okay, so what you are getting here, you have SO2AR, carbon, you have R, hydrogen, and here you are getting OAC. OCOCH3 means what? OAC. Okay,
Okay.
done.
Yes, sir.
Now this SO2AR is basically a very good leaving group. Okay, so next step what we are giving? Next step we are giving sodium amalgam. So similarly, what is the nature of sodium? Sodium is a metal, so it will donate one electron. Okay, sodium donates one electron. So basically this SO2AR, so you can think like this, that you have one odd electron is attacking here. Okay, SO2AR group is leaving from here, or you can think systematically like that first of all SO2AR group is leaving from here. So once it leaves from here, carbocation will form here, right? Positive charge will form here, and if you give now sodium, so initially you will get radical, and then if you use two equivalent of sodium, so that time what you will get, basically you will get this
Negative.
negative charge, right? So like your what Barch reaction. Okay, so you are getting negative charge here, and once you get the negative charge here, negative charge will back, OAC will leave. Okay, OAC will leave, but keep in mind, okay, you will get here E alkene, not cis alkene, trans alkene you will get here. Okay, trans alkene you will get, not cis alkene. Here this is you can do like this also, otherwise you will think it's a cis product. You can write down R this side, hydrogen this side. Okay, basically if you have carbon, so there is no fixed position of R and hydrogen, because it's a sp3 hybridized atom. Okay, anything can be present, but ultimately when you are getting your product, you are getting E alkene. Okay, so Julia olefination means you will get always E alkene. Clear? Any doubt?
Clear, sir.
Clear, right? Okay, I'm giving one question, try to solve it, then it will be done. Okay, so suppose you have methyl, then you have here SO2PH. So number one, they have given butyl lithium. Okay, butyl lithium. Number two, they have given hydrogen carbon double bond O. This. Okay, number three, you have MESO2Cl. Okay, and number four, you have sodium amalgam. Okay, try to do it by yourself, otherwise I will do. Okay, so very easy reaction. First, do step by step, no need to hurry, do step by step. First of all, you have butyl lithium, so think what you have to do. After getting the first step, then you have aldehyde, so what you have to do, then after attacking there, you just do step by step, try to do. Like, don't think about the product from now, you just do step by step, automatically you will get your product. Okay, organic chemistry you have to learn systematically, otherwise you cannot learn. Okay, if you hurry, so you will do mistake.
Alkene formation.
Alkene formation, what you are getting?
Methyl double bond C.
Methyl
Double bond C.
cis or trans, what you are getting?
Trans.
Right? So butyl minus lithium plus, right? So first of all, you have to abstract the acidic proton. So this is your acidic proton, right?
Yes, sir.
So butyl minus is abstracting the proton from here. Okay, just a minute, just 1 minute. हाँ बोलो. हाँ ठीक है, आता हूँ, रुको. हाँ आ जाऊँगा. कब है शो, कब है? 6:30 कैसे जाओगे? ठीक है, आता हूँ मैं जल्दी. कौन सा मूवी है? ठीक है, जाता हूँ. ठीक है, शिवाजी महाराज के जाऊँगा, 2 हफ्ते बाद जाऊँगा, आने के बाद घर से. ठीक है, बुक करवाता हूँ मैं। या फिर इस्कॉन जाओगे? अच्छा ठीक है, करो, मैं आता हूँ ये। हम्म, ठीक है, तुम करो, मैं आता हूँ। हाँ, 5 मिनट दो मुझे। हाँ ठीक है, मुझे 5 मिनट दो, मैं बताता हूँ। हाँ। हम्म, okay, sorry. Huh? So what we are getting, butyl minus is abstracting the proton from here. So what I will get, so here I am getting methyl, then you have here what, SO2 pH. So you are getting negative charge here. Okay, now what I have this aldehyde. So write down this H double bond C. Okay, so negative charge will attack on this aldehyde, this bond will break. So what I will get, so methyl is there, SO2 pH keep here in this side, SO2 pH. Okay, now here what I have, carbon. Okay, here I am getting O minus, here I have hydrogen, this this. Okay, next what I have,
O
MESO2.
minus
What will do?
Me2SO6, MESO,
Huh.
Cl will leave.
Basically O minus will attack here, this bond will break, again it will come back. Chlorine is a good leaving group, so it will leave from here. So what I am getting, methyl. Okay, here you have SO2 pH, and here you are getting O, SO2 Me. Next step is what, sodium amalgam. So you can think this is a leaving group, it will leave from here. Once it leaves, you are getting what, carbocation here. If you have sodium, sodium will donate electrons there, and ultimately what you will get, negative charge here, like you, similar to your Barch reaction. Okay, similar to your Barch reaction, it is leaving from here, so you are getting positive charge here, sodium is donating electrons, so you are getting negative charge here. Once you get negative charge here, what will happen, this negative charge will donates back the electrons, SO2 pH will leave from here. Ultimately what you are getting, Me, this thing. So that will be your final product. See, these hydrogens, they are trans to each other. Don't do product like this. If you are doing like this, suppose you are getting double bond here, then you are drawing methyl this side and this side. So that means what, this hydrogen and this hydrogen, they are becoming cis to each other, so that is not possible. Okay, the hydrogen should be trans, and here the alkyl group, this methyl and this alkyl group, they are also trans to each other, so you will end up in your E-alkene. Okay, you will end in your E-alkene. Clear?
Yes, sir.
So that is the end of our name reactions. Okay, next we will start chemistry of carbonyl compounds from next week. Okay, before that, okay, one more thing I want to say, that okay, start revising your organic chemistry from whatever we have started, stereochemistry or reaction intermediate. Okay, reagent chemistry, revise all the things, we will practice a lot of questions. Okay, and after finishing this carbonyl compounds and reaction mechanism, we have two more vital things in our hand. One is your this carbonyl compounds. Okay, another one is your reaction mechanism. So if we complete these two things, you can think that your 80% of your organic chemistry is done. I'm talking about only organic chemistry. Okay, 80% organic chemistry done, and this pericyclic chemistry, heterocyclic chemistry, they hardly ask 2 to 3 questions. Now they can ask anything. I'm not predicting anything, but yeah, this is the core of your organic chemistry. Okay, this GOC, stereochemistry, then you have what, reaction intermediate, then you have reagent chemistry, then you have name reactions, after that you have carbonyl chemistry, and then reaction mechanism. If you have done up to this only, reaction mechanism, then also you can score well in your organic chemistry portion. Okay, and nowadays questions are pretty much unpredictable in NET exam. Okay, so don't skip anything. I will prefer that please focus on organic chemistry. If someone is from physical chemistry background, so try to learn the organic. Okay, it will save you. Okay, if you are from physical background, definitely your physical portion is strong, but don't skip organic. Okay, because organic is scoring. Okay, if you do it, you will get it. Okay, but the thing, you have to give time in organic. Okay, it's not like your inorganic chemistry will have some formulas and you will apply it. It's not like that. Organic chemistry needs practice and it needs time, so you have to invest the time, otherwise you cannot do it. Okay, ultimately question answer practice we have to do, that we will do. Okay, and test I will take separately later. After finishing that, I will share the test in the group, so you can attempt the test based on that. But first of all, I have to complete up to here, then only I can take test. Okay, but yeah, from name reactions and that reagent, I think, yeah, name reactions I will take test. Okay, I will mention in the group accordingly. Fine. Okay, and organic spectroscopy also is covering, so that will be pretty much enough for your NET exam. Okay, fine. Any doubt?
No,
No,
sir.
sir.
Okay, Sampriti, any doubt?
No, sir.
Okay, okay, then bye. Okay, study well. Okay, all of you study well, because only I think 1 month is there. After that you have exam, right? So study hard. Fine. They have not
Yes, sir.
released anything, but I am sure they will conduct the exam in the mid of your June. So you can consider that June 15 is the last date. Okay, this date you can follow. Before that, they can, 1 week before they can conduct, 1 week after they can conduct, but yeah, you can safely you can follow this June 15. They have not released application form, they have not released anything. Okay, but suddenly they will release and they will do like that. Okay, so yeah, uh, safety first, you just prepare your June 15 for June 15. Okay, fine.
Yes, sir.
Yes.
Okay, bye. Thank you, study well.
Thank you.
Hmm.
Thank you, sir.
Yeah, thank you.
Thank you, sir.
Thank you.